through a good amount of acids and bases. And like I said, the acids and bases, really everything we've done with equilibrium, we didn't really talk a whole lot about equilibrium last time, but everything we've done with equilibrium was just going to be applied to acids and bases. So all of these problems follow the same general format. You're generally given some initial concentrations, and you want to find the equilibrium concentrations, and using the equilibrium constant for whatever type of process that is, you're then going to determine the equilibrium constant of these solutions. And so last time we had a lot of extra definitions, right? So we talked about acidity versus basicity and the different scales that we can use to determine that. So in terms of concentration, how did we define acidity and basicity? Yep. We determined it in, this should be acidic, the H3O concentration, and then basicity was in terms of the OH minus concentration, right? Those are two ions, right? So just like with solubility product, equilibrium is determined by two ions that dissolve in solution. Here, it's the exact same idea, except basicity or acidity is determined by two ions that are hydronium and hydroxide in solution, right? This is just how we define something being basic or acidic. And we can look at it from two perspectives, right? We can look at something that's acidic from either the OH minus concentration or the hydronium concentration. And then for something that's acidic, what does that mean for these relative concentrations to each other? What are we going to have more of and what are we going to have less of? Yep, we're going to have less OH minus and more H3O plus, right? We're always going to reach a special ratio, which is what ratio? These two concentrations. How do you know how much you have of one if you have the other? Right, let's say I'm given the H3O plus concentration. How do I know how much OH minus concentration I have? Yep, you use the equilibrium constant for autoionization of water, right? That's saying that the amount of H3O plus and OH minus in solution, those actual concentrations can vary. That's an acidic or basic solution, but the product of those two concentrations has to be equal to the same thing, right? And they have to be equal to Kw, right? That's always the case for a given temperature, right? For a given temperature, those are always going to be equal to Kw. And what about for a basic solution? What do we can say about the relative concentrations of both of those solutions? Arlene? Yeah, we have more OH minus than we do H3O plus, right? So if we have something acidic, we can say that, okay, we either have just a little bit of OH minus, because that's the same thing as saying that we have a lot of H3O plus. Why? Because the product of those always has to equal Kw. And for basic solutions, it's the exact opposite. We have a lot of OH minus, which is the exact same thing as saying we have only a little bit of H0 plus. Why? Because for those two numbers to be multiplied to equal the same constant in both of these cases, you have to adjust whichever corresponding concentration you haven't changed at all. Right? If you change one to go up, the other one has to go down. Right, so that's how we determined acidity and basicity in terms of concentration. We talked about that kind of towards the end of last Thursday. And then last time we started talking about defining different scales that gives us relative order of magnitudes of these concentrations, right? So these are the P scales that we were talking about. And so these were, we talked about a couple different ones. these tell us order of magnitude, meaning that they give us, as we go from one number to another, we get a factor of 10 changing, right? So these are relatively large changes in the concentration. That's because generally we're dealing with very small numbers for concentrations of solutions. And so if we had an acidic solution, how did we define the acidity or basicity for an acidic solution using AP scale?
Is it like negative log?
Yeah, negative log of the concentration, right? And what was that scale called? pH, right? That was the pH scale. And that was equal to minus the logarithm of H3O plus. And so, again, the logarithm just acts in that it takes the value of the exponent. We put a negative there because all of these are generally very small exponents. They don't go larger than 1. We put a negative sign there to cancel out the negative sign in the exponent. That tells us how big the exponent is, right? 10 to the power of what? So 10 to the power of minus 7, for example, and we take minus the log, that gives us 7, right? If we go to 10 to the power of minus 9, now that gives us 9, right? So if we have something that's changed pH going from 7 to 9, that's changing it by 100 times, right? That concentration hasn't changed by a number 2 or a factor 2, it's changed by 100 times larger or smaller than what it was before. Right, so these are just arbitrary scales. These people just made these up to give us a relative idea. They're like, oh, we can analyze these things in terms of these scales rather than having to deal with the concentrations all the time. And so this is where like that extra step comes in with equilibrium, right? Because all the other equilibrium questions, you're always asking, what are the equilibrium concentrations? Now, with acids and bases, you're not going to be asking, what's the equilibrium concentration of H3O plus? They'll say, what's the pH of that solution? And so all that means is once you have H3O plus from your ice table, you're just going to plug it into your pH value, right? So it's just one extra step to everything else that we've been doing for the last month, right? And if we have a basic solution, right, what was the scale that we used to determine the basicity of a solution? POH, right? POH, so that was our POH scale, and that was minus the log of OH minus, right? So now we're looking at the concentration of hydronium, and that gives us the OH minus scale. And these two things are related to each other, right? Because everything is related to this equilibrium constant for acids and bases. So really, we can still define an acidic solution in terms of the POH, right? It's just that it's going to be the opposite trend as what it is for the pH, right? So these two things were related to each other, right? And how are they related to each other? Does anyone remember? How are the POH and the pH related to each other? They both add up to 14, right? So the pH plus POH equals 14, right? And where does that come from? Well, if we think about the fact that the water autoionization equilibrium constant for water is 1.0 times 10 to the minus 14, that's what gives us the limit on this scale. That's saying once we reach 14, right, then the other one basically has to effectively be 0 or so close to 1, for example. And so that's why we can always analyze this in terms of the OH minus concentration, H0 plus concentration, or the pH or the POH, right? Because these two things are actually equivalent, right? The expression for Kw and this expression right here are identical to each other, right? We just took the logarithm of the expression for Kw to get this. And so because here we're multiplying two concentrations, when we take the log of something that's multiplied, it splits up into a sum, right? Log A times B is log A plus log B. That's just the pH plus the POH in this solution. And so as 1 becomes smaller, right, for this this solution becomes more acidic, right? So the pH approaches 1. The other one has to become larger for an acidic solution. That's why we have opposite trends here. pH goes to 1, that means this has to go to 13. Small pH means that we have an acidic solution, we have a large H3O plus concentration. That's the same thing as the pOH being high, because we have a small OH minus concentration, which gives us a larger pOH, right? And then if this is small, for example, then H0 plus. If this is small, H0 plus has to go up. Right, so all of these things, we're just saying the exact same thing in a different way. So that was the how we can determine the acidity or basicity of a solution based off of the concentration of H3O plus and OH minus in solution. So this was generally, you can do it for weak acids or strong acids and bases, right? So this is weak acids, bases, or strong acids and bases. Okay. And then we talked about determining for weak acids and bases, what does that mean in terms of the dissociation or the protonation or the ionization of whatever process we were looking at. So for weak acids and bases, we generally had two equations. We had our acid equation and our base equation. Our acid equation, we should always end up with what on the product side? H3O plus, right? That's what makes our solution acidic, right? So we have HA. This reacts with what? Water. HA is our acid. That's what we're going to use to be a generic acid to give us H3O plus and A minus. And A minus, what do we call that in this reaction? If this is our acid, what is A minus? Conjugate base, right? After we've deprotonated our acid, we donated the proton, we end up with the conjugate base. Which means that the equilibrium constant going in this way gives us information of the equilibrium constant going in the opposite direction. We came up with a relationship for that as well, but we'll talk about that in a second. And then the base equation, generally how it's written is if we have our generic base, this will react with water, and then what should we have on the right? What product should we have on the right-hand side of this equation? OH minus, right? Because we should always end up with hydroxide, because that's how bases work, plus HB plus. And so when we're dealing with acid-base equilibrium, we should always make sure that we can write one of these equations for whatever acid we're given or base we're given, right? If we can write this, then we can set up our ice table, right? Because the relative strengths of these weak acids and weak bases were determined by their equilibrium constant, right? The same way if we said something was very soluble, a solid is very soluble, its solubility product is going to be larger because we're going to have more of that ion in solution. Here, if something is more acidic, if it's a stronger weak acid, right? So I know that's a little counterintuitive to think about, but if it's a stronger weak acid, you're going to have more A minus in solution, and the equilibrium constant should reflect that. All right, so the equilibrium constant for acids we called Ka. And what is that equilibrium constant for this acid equation? H3O plus, A minus, over HA, right? We don't include H2O because it's a liquid, right? We don't include H2O there. And then for the base equation, what would this be? KB would be our equilibrium constant for the base equation. OH minus, HB plus, over B. And one thing to kind of keep in mind, how problems can kind of throw you off, is that this equation going in the reverse is just a base equation. The only difference is that you're starting with a negatively charged base, which is a lot of times what you use when you're making buffers and stuff in the real world, right? So instead of B right there, we would have A minus plus H3O plus, or something that can accept the proton, to then create OH or H2O, OH minus plus, it would just be HA in this case. Right, so these equilibrium constants, if we have something that is a strong weak acid, right? So for a strong weak acid, Ka strong versus Ka weak, how should these two values compare to each other? What do you think that means for the dissociation or the donation of that proton off of HA?
More dissociation with the strong acid.
Yeah, you should have more dissociation with a strong, weak acid, right? So should this be larger or smaller than?
Larger.
It should be larger, right? So this should be larger than the equilibrium constant for the weak acid, right? That means that if this is larger, we have more A minus and H2O plus relative to the protonated version of the acid compared to the weak acid. Right, so this should be larger for the strong weak acid. And the same thing for the base equation, right? We have that Kb for a strong weak base should be larger than Kb for a weak base. And like I said, that's a little counterintuitive to think about. Why is that cut off? But the reason we say things in that convoluted way is because a weak acid or a weak base, what was the definition of that compared to a strong acid and a strong base?
Doesn't completely dissolve.
Yeah, it doesn't completely dissociate in solution, right? So even if 99% of it, or no, well, 99, let's say 95% of it does dissociate in solution, it's not 100%. So that's what makes it a weak acid or base, right? Because it's not creating 100% OH minus or 100% H2O plus, we consider that weak, even if it's 95%. Strong acids and bases are defined where every time you put one molecule or one mole of that molecule in solution, you create one equivalent of OH minus or H3O plus, depending on the amount of it you're releasing in solution. Right, so we saw for bases, for example, metal hydroxides will sometimes have more than one hydroxide ion. And so, then we had a way to classify the relative strengths, right? So pH, POH told us the amount, right? How acidic or basic a solution was, just based off of H3O, OH minus concentration in solution. we also had a scale to determine the relative strengths of weak acids and weak bases, right? So we had another P scale. For strength of weak acids and bases, right? And how did we determine the relative strength of those?
The concentration was higher or lower than 1 times 10 to the 7. Right.
That was, we're looking at the pH. The pH and the pOH told us how if a solution was acidic or basic. This is going to follow a similar idea, right? It's going to be, they're going to be related to each other in some way. Yeah, it was the PK and the PKB scales, right? So that was another P scale. And this is looking at the relative strength of a weak acid or base, right? So it was the pKa, and then it was the pKb for bases. And how were those defined? Yep, it was minus the log of Kb for the pKb and minus the log of Ka for the pKa. Alright, so the same way we use this logarithm to give us a relative order of magnitude of H0 plus and OH minus in solution, which is how we define pH and pOH. This is giving us a relative order of magnitude of the dissociation of the weak acid or the weak base. Right? Here we say, okay, well, a strong weak acid should have a larger Ka value than a weak acid, right? Which means that this ratio should be larger. We know these values are like 10 to the minus 14 to 10 to the minus 2, right? So the pKb is telling us what's the value of the exponent and how is it modified between 0 and 1 for the ratio of the conjugate base for the weak acid and the acid itself, the weak acid. All right, so this is another way we're just using these numbers to give a gauge for how strong or weak a weak acid or base is. That's going to be, I know that you guys are probably looking at this like, what the hell, that's a lot of going back and forth between H0 plus, OH minus, HA, HB, B plus, HB plus. So I'm going to try my best to be very clear on the language here. The idea is that everything is very related. If you have one thing, you can pretty much determine everything else from that one thing for all these relationships. And so these were the relative ways that we determine the strength. All right, so if we have a weak acid that's strong, what do you think its pKa value should be? What do you think these values are going to be between? pKa's and pKb's. Almost 1 through 7, right? So you're on the right idea when you're thinking about neutrality, but we can go a little bit past 7. We can go to 14, the same way we did for pH, right? And to be honest, you'll see pKb and pKa values that go up to 60 and stuff, because there'll be stuff that just doesn't want to dissociate its hydrogen. That's what those are generally talking about. They're not really acids or bases at that point, but for most weak acids and weak bases, it'll be somewhere between 1 and 7, because that's going to be related to changing the pH of the solution, right? And the reason that these are going to be between 1 and 14 generally for weak acids and weak bases is because, so the pKa plus the pKb were also going to be equal to 14. And the reasoning for that was because of our other relationship was that the Ka times the Kb is equal to, does anyone have any idea what that's going to be equal to? Kw, right? Let's see, well, where the hell did Kw get? This one was, a little bit trickier of a rationale for why we get that relationship. And it had to do if we have this equation HA plus H3O plus goes to H2O plus A minus, then we have the reverse reaction, A minus plus H3O plus, sorry, A minus plus H2O goes to HA plus OH minus, right? Since the conjugate base acts as a base, right? It can take a proton from water to create OH minus in solution. Even though this is the conjugate base of the weak acid, it still acts like a base. And if we have both of these reactions that are going on, right? If this is 1 and this is 2, K1 is equal to H3O plus A minus over HA. K2 is equal to OH minus HA over A minus. So these are the two equilibrium constants for these reactions. And if you multiply these together, what happens? All right, if we multiply them together, I forgot the concentration sign down here. HA will cancel with HA, and A minus will cancel with A minus. All right, and all you're left with is H0 plus times OH minus, which is equal to your water equilibrium ratio. Right, so this one we didn't derive it from something. This was realizing that, well, if this acts like a base, then this also has to be true. This should be a liquid. And again, go ahead.
The first one,
Mhm.
the H3O plus and the H2O supposed to be on that side?
You're right, I switched to H2O. Thank you. H2O liquid plus H3O plus. Good catch. Yep, so now it makes sense with all the equilibrium constants. And so for weak acids and weak bases, what this means is that if you have the Ka for the weak acid, then you have the Kb for its conjugate base. Right, so this is the relationship between an acid and its conjugate base, or a weak base and its conjugate acid. So this is the relationship Ka for weak acid and its conjugate base. And vice versa, right? If you have the Kb for a base, a weak base, then you have the Ka for its conjugate acid. And this also means that you have some relationship between the relative strengths, right? If you have a strong weak acid, it's going to dissociate a lot. That means that its conjugate base is going to be a weak base, right? Because these exponents, right? If you have something with a low pKa, that means its pKb, or how strong its conjugate base is going to be high, right? So that's going to be a weak base. So the same way we thought about the inverse relationship between H3O plus and OH minus for acidic and basic solutions. We have the same thing for weak acids and weak bases, right? Where they're gonna be inversely related for their conjugate pair, right? A weak acid is going to have a strong weak conjugate base. And again, this is all just to add like 1 or 2 extra steps to all your equilibrium calculations. So for example, if someone's mean, they'll say, okay, here's your weak acid. The Kb for its conjugate base is this. And then, okay, well, I have to realize I convert my Kb to my Ka, and then they'll say, well, then what's the pH of that solution? So I get my equilibrium concentrations. One of those concentrations is H0 plus, and then we use that to find the pH of the solution. Okay, so that's pretty much everything important that we ended with last time, were these relationships, right? Our definitions of the pH, POH, and all of their relationships, and then the KW as well. Right, so it's like, and if you look at the equations that are given to you on the practice exam, all of those are given to you, but you see there's just like one chunk of like acid-base equations, and those are gonna be those 4 equations, right? So that's how we go from one thing to the other. You can always go from one to the other based off what you're getting. And the tricky part just comes when you're mixing it now with equilibrium and determining the pH of solutions. Okay, all right, any questions on any of that? Okay, so here we have lactic acid. It's a weak acid found in sour milk. So I skipped ahead a couple slides. I'll go back and go over them if we need to in a bit. And it has a pH of 2.75. What is the ionization constant for this acid, and what is the degree of ionization, right? So it's like, okay, we talked about all these equations. Now it's asking us specific things about what we can use those to then calculate. So if we're given the pH of the solution and we want to find Ka, right, we're given a weak acid. We can then use H3O plus, the concentration of the lactic acid in solution, right? So the pH of the solution gives us a relationship for the equilibrium H3O plus. We can then use that to find the Ka for the acid, because if we know the molarity or the initial amount of weak acid we put in the solution, we can then find the equilibrium amounts of lactic acid that are still present to then solve for Ka. And once we have Ka, we can then look at the degree of ionization, which is just going to be the ratio of weak acid to weak base. So the first step for any acid-base equilibrium problem, or where I generally start, is to write the equilibrium or the reaction that this weak acid has when you put this in solution. So what would this reaction be? We can leave it in terms of a generic weak acid, or we can leave it in terms of, in this case, what is it, lactic acid. So that's the first step, is write the acid equation because we're dealing with a weak acid for this example. Write the acid equation. I wonder if that's why. So what is the acid equation for this?
Lactic acid plus H2O.
Yep, lactic acid plus H2O. Whenever we're doing the acid or base equation, you're gonna be adding whatever acid or base you have to water to then create the appropriate ion in solution. Acid, we're gonna create H3O plus hydronium. So this will be H, I'll leave it in terms of H5O3, that's our aqueous acid, plus H2O, liquid, goes to H3O plus, aqueous, plus C3H5O3 minus. All right, so is everyone comfortable with that? All right, so this is what we talked about even last week, where we define our conjugate acid-base pairs, right? All we're doing is we're writing the reaction with water to create, whether it's weak acid or base, hydronium or hydroxide in solution. All right, so the next thing we're gonna do is we're gonna set up an ice table, but we're gonna see if we can fill in values in this ice table before looking at the equilibrium concentration, right? Because so this problem, because you're given the pH of the solution, that tells you something about an equilibrium concentration already. So you're not just being given initial concentrations here. All right, so we have initial, change, and equilibrium. And then water, we're not going to be worried about because it's a liquid. So is there anything that we can fill in right away?
The lactic acid.
We can fill in the lactic acid because it gives us the concentration of lactic acid, right? 0.025 molar lactic acid. And we put that in solution. Initially, we have how much H0 plus in CH3, or lactate, right? Lactate is the conjugate base of lactic acid. How do I know that? Well, if it's a negatively charged ion, you play lactic acid with just ATE. You guys will learn all about that next semester. Okay. How much H0 plus and OH minus should we have when we first mix this solution with water? 0, right? And is there anything else we can fill in?
Our change.
We can fill in our change, but we can leave it into some arbitrary term as X, but because we're given something about an equilibrium concentration, we actually know exactly how much of everything, all the changes are in solution. And so what else are we given in this problem, right? So we know this right here is an initial concentration of HA right, our weak acid. Can we fill in any of the equilibrium values? What is the pH related to?
It's related to the amount of, like H3O in the.
Yeah, it's related to the amount of H3O plus in solution, right? So if you're given a pH, that's related to the equilibrium concentration of H3O plus. Why? Because the pH scale is defined when we look at the ion and water product constant, right? The equilibrium of autoionization of water. This is a relationship to the equilibrium concentration of H3O plus. You can say, well, how am I supposed to know that? Well, if you have 0 H3O plus before you mix things together, right, then there's no pH defined for that solution, right? If you have 0 H3O plus, there's no pH defined, or it sets a limit at right, there's no pH defined for that. So the only way we can have a pH is if we have some equilibrium concentration of H3O plus with whatever the acid we put into solution. So whenever you're being asked to solve for pH or being given a pH, that's telling you about the equilibrium concentration of H3O plus. So that means that if we have pH is equal to minus the log of H3O plus, how can we get the concentration of H3O plus at equilibrium? So that is going to be related.
Do you take the E to both sides? Or?
If it was a natural logarithm, we would, and you could do everything in natural logarithm, but pHs are defined in log base 10, right? So this is log base 10, all of these logarithms, which means that if you take both sides to the power of 10, that'll cancel out the logarithm on both sides, or on the logarithm here will be canceled out. We can bring the minus 1 to both sides as well to cancel out the minus 1 there, which means that if you have 10 to the minus pH, that's equal to the concentration of H3O plus. And it means if you're given the POH, that 10 to the minus POH gives you the concentration, the equilibrium concentration of hydroxide in that solution as well. So this, in this case, is equal to 10 to the minus 2.75. If I plug that in, 10, 2.75 minus, I get 0.002 molarity H3O plus. So I know this is going to be 0.002 molarity. Right, so the trick here is just that the pH is related to the equilibrium concentration of H0 plus. When you're actually solving for equilibrium concentration, small x, big X, doing all those types of things, you won't be given the pH for that solution. You'll be asked to find the pH of the solution. So giving the pH of a solution is like the same thing as giving the equilibrium concentration. And so can you use these? You have one equilibrium value and all the initial values. Can you find all the equilibrium values here?
Yeah, because they're all 1 to 1, right?
And that's what's nice about acid-base reactions, that everything is 1-to-1 ratios. Right, so once you have this, then you should be able to fill in the change here. You know the change here, you know the change there, and you know the initial change. So why don't you guys take a second, see if you can fill in the rest of the ice table. Those right here.
Plus 0.002.
right, plus 0.002 molarity. What about here and here? Same thing, plus 0.002 molarity. This is just going to be 0.002 molarity, right? Because 0 plus that gives us that value. And what about for the reactant side here? What's the sign for that going to be? It should be minus because the reaction is moving to the right. 0.002 molarity. So our final equilibrium concentration should be 0.023 molarity. Right, and so if we see, here we're actually using real values, and we think about when we make our x's small approximation, you can see that this change value is very small compared to the initial concentration that we started with. So based off of that, it's not extremely small, but it is kind of small. What would you expect for the Ka here? Do you think it's going to be a large Ka or a small Ka? I would expect it to be somewhat small, right? At least compared to the original concentration. So then how am I going to find the Ka for this? What do I do? What if I just solved for, what was the whole purpose of doing this step?
To be able to put it into your acid equation.
Yeah, to be able to plug it into my expression for the equilibrium constant, right? And what do I plug into my expression for the equilibrium constant?
K equals our aqueous products over our reactants.
Yep, Ka is going to equal, right, so 3, we're going to find Ka. Ka is equal to H3O plus C3 H5, what was it? O3 minus over HC3 H5O3. And what values do I plug into that? Yeah, we plug in, the whole point of doing all of this was to solve for our equilibrium concentrations so that we can then plug that into our expression for Ka, right? Since we're given the numerical value of one of the equilibrium constants, we know what the initial concentrations are, we can solve for the rest of the equilibrium concentrations. So we can plug in, this equals 0.002, 0.002 divided by 0.023. And that'll give us a value for Ka. So if we get 0.002 squared divided by 0.023, we get Ka equals 1.7 times 10 to the minus 4. Right, and so this value, it's not super small, but it's small enough that we could probably make a small x approximation here, because these changes on the way to equilibrium are small. If we had to, if we're going the other way, not given an equilibrium concentration. So that gives us the value for Ka. So how are we going to find the percent ionization here? All right, so the last step, once you guys are finished catching up, we'll look for the percent ionization. So in terms of our equilibrium constant, does anyone see anything that would look like percent ionization? Our percent is just a fancy way of taking a ratio, right?
Would it be the, like, dividing by 1 times 10 to the negative 14 or something?
We're gonna use this value for sure for that. Because once we have this value, we can then look at the relative amounts of lactate and lactic acid, right? So if we look for the percent ionization, that's the ratio C3H5O3 minus over HC3 H5O3. If we're being extremely accurate, you could say that this is equal to this plus whatever amount you have there. But this will give us a good enough answer to look at the percent ionization because we don't ionize a whole lot. And so if we have Ka is equal to H3O plus CH3 C3H5 O3 minus I wish I stuck with the generic acid base form right now. I'm tired of writing this over and over. We can divide both sides by H0 plus, our equilibrium concentration. What happens to it on the right-hand side of this equation? Cancels out. Which means that Ka over H0 plus equals the ratio that we're looking for. And we know this ratio is related to the percent ionization. This will give us some small fraction. We multiply that by 100, and that'll give us the percent. H3, HC3, H5, O3. So it's 1.7 times 10 to the minus 4 divided by 0.002 gives us 0.1237 divided by 0.002, 0.085 times 100 gives us 8.5% ionization. So I think there's a couple questions on the problem set that ask, what's the percent ionization? That just means that you're just looking at the relative amounts of weak acid or weak base and their conjugate base or conjugate acid.
Degree and percent using.
Yeah, you can use them interchangeably. If it asks for degree, generally you leave it as a fraction, but if you did the percentage, that's just an extra step. Because it's not asking like in degrees, like in angle degrees, it's saying to what degree is this been ionized, is how that's phrased. Alright, so here we didn't have to solve for any equilibrium concentrations, except for the ones that we had to fill in on the ice table. We were given the equilibrium concentration, not exactly given it, right? It wasn't like, here's the H0 plus concentration. There was one extra step. It said, here's the pH, right? And you have to use that to find H0 plus, which you then plug into our relationship between pH and H0 plus to then fill in the rest of the equilibrium concentrations. Once you have all of those, you can determine the ionization constant for this acid. All right, so this is the same thing where you're given the molar solubility right? And you can use that to solve for KSP. Because that's related to these values here, the equilibrium concentrations. Same thing, just different look. All right, any questions on that? Lee?
So degree of ionization is conjugate base over acid?
Yeah, it'll be conjugate acid over base, right? If you have the base equation going the other way. That's always what that means when that's asking for that. And I remember when I was a student that when I saw ionization, I separated ionization from acid and base equilibria for some reason. But this is all we're looking at, right? We're just looking at the concentration of ions in solution. Those ions just happen to be how we define acids and bases. Right? And all these problems are the same. It's aqueous ionic equilibria. Right? It's just an extra step. Use pH to solve for concentration. Or given the concentration, what's the pH? All right. So here, you're given Ka, and you're asked to find the pH of the solution. So what do you think is different from this problem versus the last problem? All right away, let's see what do we recognize as the difference here? You're not given the pH, and the pH gave you what in the last problem? What do we use it for? Equilibrium H3O plus, right? Which means now, since we want to find the pH, we have to find the equilibrium concentration, right? You're still given some concentration of a weak acid, right? And so this is going to give you what for the problem? What is 0.1 molar going to give you here? What did the 0.025 molar give you in the previous problem? That was the initial concentration, right? Because this is saying before I even ionized any of it, that's how much I put in the water. All right, so that's your initial concentration. So this gives you your initial concentration of acid. Does that give you your initial concentration of H3O plus and A minus? Right. Those should be 0, right? Because if you have this initial concentration, you know before it ionizes it all, you should have 0 of the other ones. The difference here is you don't know what the equilibrium concentrations, right? So in problems in equilibrium, if you want to find the equilibrium concentration and you're only given initial concentrations, what else do you need? If you're only given initial concentrations, what else do you need for that problem to find your equilibrium concentrations? Here, what are you trying to find the equilibrium concentration of? So what is the question asking you to solve for? Yeah, it wants you to find the pH, right? And the pH is related to what? H3O plus concentration, right? So you want to find the equilibrium concentration of H3O plus to then get the pH, right? If you're given initial concentrations and no equilibrium concentrations, what else do you need to have to be able to solve for equilibrium concentrations? Right, so you're given, this tells us initial concentrations, right? We need what else if you're given initial concentrations to find. So we need the stoichiometry, right? We need the stoichiometry, so we're going to need our acid-base equation. That's always what we start off doing, right? Right. In this case, it'll be a acid or base equation, you think? Acid. How do you know that? Because it's giving you that you're putting in acetic acid, right? So write the acid equation. We know that because it says acid, that it's going to be an acid equation. So that'll give us the stoichiometry. What else is related to the equilibrium concentrations? of not just H2O plus, but everything. All of your species. Ka, you need the equilibrium constant, right? When any equilibrium problem, if you're not given equilibrium concentrations, you need some sort of equilibrium constant and your initial concentrations. That's the only way that you can solve it, right? You need that information to be able to find the equilibrium concentration, right? So you need Ka, and you're given Ka here, right? So initial concentrations needed with Ka to find equilibrium concentrations. And we need the equilibrium concentrations because we're asked to find the pH, right? And the pH is related to the equilibrium concentration of H3O plus. Right, so this is ultimately what we're trying to solve for, but we need to use all the other auxiliary information to be able to get to that point, right? This is a simple equation to solve, pH equals minus log H3O plus. Solving for that H3O plus, though, in this case is a little bit more challenging. Right, so our acid equation, since we're not given the chemical formula, I'm just gonna put HA reacts with what?
H2O.
H2O. And that should create
H3O.
H3O plus, which is important because we need this to solve for the pH plus A minus. So we have an ice table. And so initially we have how much HA?
0.1.
0.1 molar. Water, what do we do with water? Nothing, because it's in a liquid state. And then H3O plus, how much do we have initially? 0. And A minus? 0. What's our change gonna be for this reaction? What's the sign of our change gonna be? Going from left to right. Right. This change, what should the sign be? Negative, because we start off with 0. Even though this is a smaller equilibrium constant, still larger than 0, right? So this is gonna move in that direction. So we get 0, or sorry, minus. What about the sign for H2O plus and A minus? Positive, because we're moving in the right direction, so we're adding to those. Positive and positive. And then what are we gonna use for the value for the change? We use just some arbitrary value, right? Because we don't know what the equilibrium concentrations are. That's what we need to solve for. So it's minus x, and plus x. So then our equilibrium values are going to be 0.10 molar minus x plus x, x and x. And so now what do we do from here?
Plug in the Ka equation.
Now we use our equilibrium values. Redo that one. We use our equilibrium values, how's it keep doing that? To then solve for, we use these equilibrium values with our expression for Ka to then solve for x. So first, we write an expression. We use Ka. So Ka is equal to what? Before we even do that, it's H3O plus A minus over HA. Now we plug in, what are those equilibrium concentrations? X squared over, right, this is gonna be x times x over 0. Is it 0, 1 or 1, 0? 1, 0 minus x. And this is why we need Ka, right? Because we need Ka to be able to plug, otherwise we don't have any numbers to solve for, right? We have nothing to solve for if we don't have Ka. So we have 1.7 times 10 to the minus 5 is equal to x squared over 0.10 minus x. Diego?
For the problem for x and x, wouldn't we just be able to like square automatically, like if we do it on an exam? Or
So you're taking the square root automatically?
yeah, automatically.
Yeah, so this one you can ultimately do that, and the justification for that is because this change is gonna be small, right? See, this concentration you're starting with is like 10 to the minus 1. Your equilibrium constant is 10 to the minus 5, which means you're probably not gonna move very much, which means that change, that arbitrary change, is small. So this number is smaller than that number, quite a bit smaller. So you can just get rid of that, right? So you can just make that assumption, get rid of this, and then once you multiply this over to the other side, then you can square root it, right? So that's the other step that you have to do. You have to make sure you do that in this case. And you can double check. You could also leave it like this and use quadratic formula if you want. You'll get two answers. One will make sense, one won't. And then you'll see that, okay, those two values, if you calculate it both ways, aren't that different from each other. All right, so we can use this to 0 because x is much smaller than 0.10. So when we do that, we get 1.7 times 10 to the minus 5 equals x squared over 0.10. Multiply that to both sides. What happens to it on the right-hand side of this equation? Cancels out. So we get x squared is equal to 0.10, 1.7 times 10 to the minus 5. And then now we can do what Diego said, which is square root both sides, right? That's the same thing as raising both sides to the 1/2 power. Same thing as square root. That's the exact same thing. That gives us that x is equal to 0.10 times 1.7 times 10 to the 5 minus. Then if I square root that, I get 1.3 times 10, 10 to the minus 3. If you see, so this is like 0.001, whereas this is like 0.1. So this is about less than 1% of what that value is. So that's the justification for that. This is, in my opinion, kind of teetering just on the edge of whether or not you can make this approximation. Right, and what should the units of this x be? Molarity, right? Because these represent equilibrium concentrations. So we use Ka to solve for this, and then we need to find the pH of the solution. So how are we going to use this to solve for the pH of the solution?
Just plug it in H3O.
Yeah, and if we look here, this is the equilibrium concentration of H3O plus, right? This is H3O plus concentration at equilibrium. Why? Because everything's nice in 1-to-1 ratios in acids and bases for weak acids and weak bases. So to solve for the pH, right, this is what I mean. It's just an extra step that you have to take once you have your equilibrium concentrations. The pH is equal to what? Negative log H3O plus concentration. This is equal to minus logarithm then of 0.0013. If I take the log base 10, that'll give me 2.88. And if I had to then find the degree of ionization, how would I do that? It would be exactly the same as what we did on the last problem. Yeah, Ka over H3O plus equals A minus over HA equals 1.7 times 10 to the minus 7 over 0.0013. 1.7 times 10. Dang it. 10, 5 minus 0.0013. This will equal 0.013, or roughly about 1.3%. This was the percent ionization, or the degree of ionization in the All right, how do you guys feel about that? Thumbs up, thumbs to the side, thumbs down. Okay. All right, let's take like a 10-minute break and we'll come back and we'll talk about a couple other types of problems you might see. And maybe, so again, for people who came in late, just make sure you look at the reminders. Exam on Tuesday. I'll send out another announcement for what you need for the exam and what it's gonna cover exactly. Quiz 2 makeup is posted, that's not due for 2 weeks. Again, that's a hard deadline. And then the problem sets 4 and 5. 5 is a practice exam, so make sure you look at that for the exam on Tuesday. 4 is more practice equilibrium and a little bit acid-base equilibrium. And then assignments that are due this Friday close next Friday, right? So November 1st, all of the assignments that are due by this Friday. So the last 2 assignments that follows is problem set 4 and your qualitative analysis from last week, right? So group 2 cations. And also no class next Thursday, right? So I know it's like going into lab right after you take an exam. We're not gonna have a class on Thursday, so that's kind of the makeup. You can use that extra day, hopefully, if you need to catch up on work or just take a small break. Okay, all right, so this is basically, again, the same process that we've been doing for equilibrium. The only thing is you add an extra step, right? We just have to solve for the pH. So steps 4 and 5 are the only thing that's different from what we've done before, right? Everything else up to this point is the same. And so there's a couple different scenarios that you can look at, and we're using the example of acids, but if you do this for a base, you get the exact same thing, right? You can look at a mixture of 2 strong acids, a mixture of a strong acid and a weak acid, or a mixture of 2 acids. And the mixture of 2 weak acids is going to be similar to how we treat polyprotic acids as well. So if you have a mixture of 2 strong acids, how do you think the pH of that solution will depend on the 2 strong acids? When we put a certain concentration of strong acid in solution, what's the pH? What's pH related to in general?
Lower than 7.
The H3O plus concentration, right? So it's the H3O plus concentration, and we have a strong acid that's equal to the concentration of the acid that we put in solution, right? So for a strong acid, right, we have H3O plus. So for strong acid, if I just go to the next, so I'm going to number these 1, 2, and 3. For 1, the concentration for a strong acid HA, or whatever the acid is, equals H3O plus. Right, because that completely dissociates in solution. So if you have the concentration of the strong acid, then you have the concentration of H3O plus, and then the pH is just the minus the logarithm of that. Right, so that's how you get the pH. It's a simple calculation. Same thing for a strong base as well. So if you have two strong acids that you mix together, what do you think the pH is going to be?
Just the addition of.
Yep, just the additional of both of the moles of strong acid that you add, right? So for two strong acids, HA1 plus HA2 equals the total H3O plus concentration. And so once you have that, then you have the pH of the solution, right? Because once you have this you just plug in the pH for solution. And generally when you do this, if you're mixing two different volumes of two different strong acids together, you have to convert things to moles, then divide by the new total volume, right? So, but that's same standard stuff that you guys have seen when you've done this before. So this is, just make sure, sometimes usually find the moles of each strong acid, then find the new concentration, right? So to get to that first part, you need to find the new concentration by dividing the moles by the new total volume, right? M1V1 equals M2V2. Right, so if you have two strong acids, the sum of the moles of both strong acids gives you the total moles of H0 plus divided by the new volume, gives you that concentration. That you then plug into minus the logarithm to give you the pH of that solution. Right, so two strong acids, two strong bases are generally very simple, right? They don't modify how we operate at all, right? We didn't really need ice tables or equilibrium to understand that. All right, am I good to go on to the next? For a strong acid plus weak acid, how do you guys think this will affect our calculations?
Would the change in the weak acid be like negligible?
It'll be small, and you will find that it is negligible. So it's not 100% negligible. So it's not like we can just ignore it completely, right? But it will be. It can be negligible, right? And so this is going to be related to. So maybe this will give you a hint. If it's related to the common ion effect, when we add strong acid and weak acid together, the strong acid does what? How do you define a strong acid? Yeah, the strong acid, in terms of, right, so HA strong, that gives you an H3O plus concentration, right? Because that's how we define a strong acid. So what you're going to do is you're going to assume that dissociates 100%, right? And then this is going to give you an initial H3O plus concentration. So the same way we looked at common ion effect with solubility product, if we had some other ion in solution, that gives us an initial concentration of some ion in our ice table, right? So a strong acid is just going to give you a source of an initial concentration of H3O plus. Because if we already have H3O plus, that'll affect the equilibrium of our weak acid. So we treat this as the strong acid as a common ion. What I mean by that is if this is our weak acid, HA weak plus H2O goes to what for our acid equation?
Be the H3O.
H3O plus A minus. I'm gonna put subscript weak again just so that we know that we're talking about the weak acid in this case, right? Question?
It would still normally go towards the products, right? Because the weak acid will.
Because you still don't have
Yeah.
any, you're not starting off with any conjugate base, right? So because you still have a zero there, right? So, and the equilibrium constant for this, A weak, is equal to H0 plus A minus over HA weak, right? So this is our equilibrium for our weak acid, right? The strong acid dissociated completely. So that just gives us H3O plus in solution. And so what that does is if we look at the equilibrium of our weak acid, now we already have some H3O present in solution, and that's gonna affect the position of this equilibrium, right? It's the same way if we had a common ion, it affected the solubility of our solid because it either forces everything into the solid phase or into the aqueous phase. Here, we're looking at two aqueous phases, right? If we already have some H3O plus, do you think that's gonna make it more or less likely for HA to ionize? Right, if we already have some of this in solution, right, how do you think that'll affect the equilibrium?
More likely to ionize.
So if we already have some of this here, right, if we add this, let's say this is already in equilibrium, right? If we add this to solution, which direction does the reaction shift based off of Le Chatelier's principle? This way, right? Which means if we already have this present in solution, that's gonna make this less likely to ionize, right? So we're gonna have even less conjugate base than we would normally because the presence of the strong acid has suppressed the ionization of the weak acid, right? And that's kind of what you're saying, well, can you just ignore it? Well, you can't exactly ignore it, but it suppresses the ionization. It's like a compounding effect. It's already not that strong compared to the strong acid, and on top of that, it suppresses the ionization of the weak acid as well. Right, so this value, H0 plus, is now the initial value in our ice table, right? We still have whatever the concentration value, the initial concentration of our weak acid, and we have 0 of our conjugate base, which is why the reaction still moves to the right, right? Because our equilibrium constant isn't 0. So Q in this case would still be, this is 0, so that's why we still move to the right. But the initial concentration is given by the strong acid. And this is the exact same thing as if we had, silver chloride dissolving in solution, and then you add sodium chloride, that chlorine ion suppresses the solubility of silver chloride. So again, same thing that we were looking at before, just different system, right?
For weak acid and weak acid, would you need 2 sets of Ka to find?
Mm-hmm. That's what the last scenario is going to be. And so those ones, unless they're relatively far from each other, meaning the values of Ka's are very different, you don't really see them. And it's basically what you said for this was going to be the case for the other one, where basically you only really care about the stronger weak acid, and then the weaker weak acid doesn't really change the pH at all. And that's because of this effect here, right? If you start ionizing a stronger weak acid, that's going to suppress the ionization of the even weaker, already weak acid. Right, so for strong acid plus weak acid, or a strong base plus a weak base, all that does is it just gives you an initial concentration of the H3O plus or OH minus. Right, so if we were to look at this for strong base plus a weak base, the strong base concentration gives you the initial hydroxide concentration. We get B plus H2O. And what should be on the product side for our base equation? OH minus, right? OH minus, aqueous, plus BHB plus. And now for our ice table, this is our common ion, right? The strong base gives us a source of our common ion, which is hydroxide in this case. So this is the initial base concentration. Water we don't care about. Our strong base gives us our initial hydroxide concentration, and this is still going to be 0, right? Our ionized base is still going to be 0, so the reaction is still moving to the right. So same thing, the common ion is going to suppress the ionization of the weak acid or the weak base. Here it's simple just because the strong base just gives us the initial concentration of our ion. The same way in the bounce back method for complex ion formation, you assume all of the products created, then you bounce back. Here we're assuming all of this hydroxide is created in solution, and then we're adjusting the equilibrium of the base, the weak base that's already there. And then the last scenario is going to be weak acid plus weak acid, or weak base plus weak base. And for this, you're going to assume that Ka1 is going to be much larger than Ka2. So the stronger weak acid is going to determine the pH of the solution. So the stronger weak acid determines the pH for a base. The stronger weak base determines the pOH. Again, we can use pH or pOH to determine the acidity or basicity of the solution. They just have opposite patterns, right, or opposite trends. And this is going to be the same for polyprotic acids. Does anyone remember what polyprotic means? Does anyone have any idea? What does it sound like? can, yeah, in a way you can think of it as multiple products. Protic sounds like what? Protons, right? So polyprotic acid is going to be an acid that can dissociate more than one proton. An acid more than one proton. More. So for example, H3PO4 can go to H2PO4 minus. That can go to HPO4 2 minus, and that can go to PO4 3 minus. Right, and as you can imagine, as you dissociate one proton, it becomes harder and harder to dissociate the next. Right? If it becomes harder to dissociate this proton than it was for this one, what do you think? How do you think those Ka values compare? What do you think the trend for Ka values?
You get
It's-
smaller.
They should get smaller and smaller, right? It's harder to ionize as this moves forward, right? So this would be Ka1. It's going to be bigger than Ka2, bigger than Ka3, which is bigger than, well, there's no Ka4 because there's no protons there. And so the way you treat polyprotic acids is you treat it like mixing two weak acids together. One is going to have a larger equilibrium constant than the other, so that one's going to dominate the pH of the solution. And it's kind of this, compounding effect too. As you deprotonate more, it's harder and harder to deprotonate the next because it suppresses the protonation by the same method having a strong acid in there did. If you already have H3O plus in there, that affects the equilibrium of the next protonation. All right, let's see if we can. All right, so those are the three scenarios for weak acids and weak bases, and strong acids and strong bases, and the mixture of them, how they can affect things. Okay, so let's look at do I want to do this one? Where'd my weak acid, strong base, or strong acid? Okay, we'll look at this one first. All right, so this is a mixture of two weak acids. How do you know they're two weak acids here? Since you don't want to do this one. I don't know if I want to do this one. How do you know there's two weak acids? If I didn't tell you that they were weak acids. Sometimes people have you memorize the weak acids, but if I give you the Ka values, you can tell that they're weak acids right away. Because, yeah, the Ka's are small, and because I gave you a Ka, right? A strong acid is going to dissociate completely. There is no Ka defined for those. So that's how you know that they're two weak acids. And so to find the pH and the conjugate base, concentration of both of these solutions, you would then just set up an ice table like we did before. And so we write our acid equation, which are already written here. So we have HNO and HNO3, and then we can set up an ice table. And for the weak acid mixtures, you just assume that the Ka for the stronger weak acid dominated or determined the pH of the solution. So which of these two has a stronger, which one of these is a stronger weak acid?
The first one.
The first one, right? So why is this a stronger weak acid?
It's 10 to the negative 4.
Yeah, this Ka is about 1,000,000 times stronger than this Ka, which means that the relative ionization is about 1,000,000 times more for this value than it is for the second weak acid, right? So Ka for HNO2 determines the pH of the solution. So that means that we have HNO2. What's our acid equation? This will be added to what?
To water.
To water. To then create what does this create? H3O plus NO2 minus. We set up an ice table. Initially of NO2 we have 5 molar. So this will give us what for our initial values? Water is liquid, so we don't worry about it. It should be 5 molar for HNO2. For H0 plus and NO2 minus, what should it be?
X, or wait, 0.
0. The reaction moves in which direction?
To the right.
To the right, because we have no products in this case. So what are the signs for everything going left to right? Minus, positive, positive. It'd be X, X, and X, because everything's a 1-to-1 ratio. We get 5.0 minus X plus X and X. Ka is equal to H3O plus NO2 minus over HNO2 at equilibrium. So we get X times X over 5.0 minus X. How might we be able to simplify this? Yeah, we can use a small x approximation because it's a small equilibrium constant, right? We're probably not going to move very far. So this is small. So this becomes x squared over 5.00 equals, then the equilibrium constant was 4 times 10 to the minus 4. We then solve for x, and that gives us the OH, or the H0 plus concentration and this pH. Deja? For acids and bases, a lot of times you are going to do small x, assuming that you don't start from some concentration like 0.00002, which I don't know why you would ever start with some concentration like that, right? Because if that was your initial concentration, right, and your Ka value is like 10 to the minus 4, that is still going to be, you know, a small change compared to this. I mean, really, even in that case, because this is so small, right, 0.002 times that, and you do square root, that one might be comparable if you started with such a small concentration. So that one could be, you know, but if you're starting from some concentration, this is like a whole number, and you know that this squared has to equal 10 to the minus 4. Mm-hmm. Ultimately, you could use quadratic formula for this too, because it would give you, it wouldn't be that much harder. It'd just be a little extra work. And so then you could plug that in, and that would give you 5.0 times 10 to the minus 4 times, or sorry, it was 4.0 times 5, all square rooted. And that would give you the equilibrium concentration. And when you do that, you get 0.045 molar, and that equals the H3O plus concentration. You use that to then solve for the pH. And then you could use this concentration as your initial concentration for the second weak acid. So generally you're not going to be asked to use that to find the pH because it won't change the pH very much. But you can use it to find the concentration of your second conjugate base, for example. So if we had our second weak acid, this was our initial concentration of H3O plus that we just solved for. This affects this equilibrium. Now we have some initial concentration of H3O plus, right? This is our base equation for the second weak acid, so the weaker weak acid. And because now you already have some H3O plus from the first much stronger weak acid, that introduces a common ion that'll then shift the equilibrium and suppress this ionization even more, right? So the second weak acid is going to be suppressed even more. And so when you do that, you can go through the same process, assume X is small, and you can find the relative concentration. So the exact same steps we did. And you see that this concentration, or the ionization of the second weak acid, is very, very small, right? The first one, the relative concentration of H3O plus from that was 10 to the minus 2, right? This is 10 to the minus 8. So this is 1,000,000 times smaller than what you get from the first weak acid, which is why you assume that one is going to determine the pH. And so for polyprotic acids, it's going to be the exact same thing. You assume the first deprotonation is the stronger weak acid. The second deprotonation is the weaker weak acid. All right, so we'll leave it for there today. So that kind of goes through everything that'll be on the exam, so we won't have any questions on buffers or anything. If we got into that today, I would have